Today, I have a conversation with Professor Martin Heck, a professor at the Photonic Integration Group at the Electrical Engineering Department at the Technical University of Eindhoven in the Netherlands. Our main focus in this discussion are the emerging trends in indium phosphide lasers. We discuss monolithic and heterogeneous integrations, process technology, and the industry ecosystem. We also discuss the advantages of quantum dots from a first principles perspective and where the industry is headed in co-packaged optics. We conclude with an enlightening discussion from Professor Heck on the role of academia in long-term technology advancement. I hope you enjoy our conversation. Please follow Professor Heck on LinkedIn, where he is quite active. As always, subscribe to the newsletter on Substack for more content like this. Now, on to the discussion. One of my readers of my newsletter recommended you to me and said, hey, you should talk to him about indium phosphide lasers. So that's why I reached out to you.
Yeah, so maybe we should do a short introduction because we met through LinkedIn, or the contact through LinkedIn, right?
Yes. Yeah, sure. I'll start actually because I do know I looked at your website and all that. But what I actually do is I write a Substack publication, which I call VIX Newsletter. And I basically write a lot about semiconductors and what's in the semiconductor industry in a very technical sense, because that's my background. I'm an engineer by training and profession. I like looking at in depth. So I've looked at a lot of stuff in RF, analog stuff like memory, processors, optics, power. I've written about all of these things. The newsletter has been growing over time. I've been doing this for about 2 years now. So now I'm kind of trying to expand my understanding and all my readers' understanding of technical fields by reaching out to experts like yourself. So that's where I'm coming from.
Okay, yeah. For me, it's very straightforward. I'm professor in the Photonic Integration Group here in TU Eindhoven in the Netherlands. We work on photonic integration, but with a focus on the 3-5, the compound semiconductors. So indium phosphide, right? Include a little bit other 3-5s. The choice for 3-5 technology is because you need a different clean room for 3-5 than for silicon. So you need to make a choice there. And a university typically has only one clean room.
Yeah.
I used to work also, I did my graduation in this group, but also I used to work in Santa Barbara, UC Santa Barbara, on photonic integration. And I used to work in Denmark as a professor, also photonic integration, but less on the technology, more on taking a fabless approach and working more on the circuit level and thinking about applications.
Okay, awesome. That's great. So I have a bunch of questions I have thought up that we could kind of work towards, but feel free to deviate as much as you need to, because we never know where the conversation goes. So in terms of indium phosphide, is that part of your current research program? Is that something you're looking at? And what's new? What's the latest cutting edge that you're looking at right now?
So, I mean, the technology is rather old.
Right.
It's the technology of choice for lasers in the telecom wavelengths, which is the reason that we work with it. That means we also work with photodiodes. We also have modulators in this material. Okay. What is new? There's nothing radically new here, right? Things are moving. Overall, things are moving steadily forward. Just like that, there is nothing really new in a lot of the other technologies. Okay. But I think the trend that is there is that we now have credible ways. So there are two things new. First of all, we have credible ways of actually going slowly towards the circuit level with companies like Smart Photonics, for example, who offer circuit level technologies. There has always been a challenge because, if you're not worried about circuits, not worried about photonic integration, you can easily, you just make a layer stack that gives you the best laser or the best photodetector or the best modulator. But the real challenge is to actually figure out how to put everything together. And then you have conflicting requirements. So that is what we call monolithic integration. That is not really new, that we have been working, as a group, we have been working for that already for 25 years. But, that hardly came out of the lab. And slowly that comes out of the lab. And it becomes available for applications also outside of telecom. So that is that is slowly getting there and in a way that is new. But the thing that is really, on everyone's radar at the moment is the whole field of heterogeneous integration. So that is, let's say, rather new. Of course, when I was at Santa Barbara, we already started that with putting wafer bonding and die bonding. There it was die bonding on silicon. So we basically try to bring this indium phosphide on silicon. For many reasons. There could be reasons that you can work on 200 or 300 millimeter wafers. There could be reasons that you want to bring combined silicon photonics and indium phosphide. There could be reasons that you want to combine silicon-based electronics and indium phosphide. So there are many reasons, but I think what is for the last few years, the really hot topic is heterogeneous integration. And that means for electronics and for photonics, it means a little bit of different things, but there's overlap. For electronics, we talk about the chiplets, right? The 2.5 3D integration. For photonics, it's maybe historically we use the word heterogeneous integration also to think about how can we bring different materials that are not lattice matched, right? Indium phosphide and silicon, how can we bring them together? What kind of techniques do we have for that? Okay. Also, chiplets are possible, flip chipping, wafer, and die bonding. Also things like micro transfer printing, etc.
Cool. I think for anybody who might read or listen to this later, I think it's interesting to understand why we have to do all this heterogeneous integration to begin with. In a sense, we can't make lasers on silicon because it is what is called an indirect band gap material. And because of that, when the electrons go from the conduction band to the valence band, they don't emit light unless they also have something called a phonon that adjusts for momentum. So that simply, unfortunately, silicon being all the great material it is, cannot make lasers, at least not effectively enough the way we want it to. So that's why you need these materials. And the best way to put it on silicon is to make it in a direct band gap material and then put it onto silicon so that you get kind of the best of both worlds, right?
Yeah. Silicon is a great technology, by the way. It's not a great material. The best transistors also are made in compound semiconductors, not in silicon.
Yes, actually, that on that note, it's the news cycles are always filled with how we're going to the 2 nanometer node. But there are so many applications, lasers being one, high power RF, all of these 3-5 semiconductors like gallium nitride, gallium arsenide, even power conversion. There are no substitutes to these materials. It has its unique uses. I guess you mentioned indium phosphide has like its roots in the telecom industry, right? So it has a pretty wide usage over time in various applications in optical communication, which has been around for a while. But right now, again, I think people have started using indium phosphide lasers for all kinds of data center based applications. And it's suddenly come into popularity again. But historically, I think these wafers have always been 3 inches or 4 inches. What exactly is that?
Many reasons. First of all, the material is relatively expensive and it's also relatively brittle, right? So, I mean, it breaks. If you drop a silicon wafer, it falls and it clings a little bit, but it survives. And indium phosphide just shatters. That is one reason. The other reason is, what are the volumes?
Okay.
And I mean, if you think about a laser, if you think about only a laser, it's a few hundred micrometers in length, maybe 200-300 micrometers in width. That's more than enough already, yeah? And then you can now think about how many lasers you can then get out of a wafer. I mean, 1 square centimeter. So if it would be one millimeter by a millimeter, get already hundreds out of a square centimeter. And you have, I don't know, with a 3-inch, 30, 40 square centimeters. So you already have for a few thousands, right?
Right. Okay.
Make it smaller. You have 10,000. You go with tens of thousands, maybe up to 100,000, but tens of thousands lasers per wafer. So that's already a lot, eh?
That is a lot. But seemingly not enough these days. That's the surprising thing. And that's why you see some people like, I think there's a company called Coherent who is now talking about moving to 6-inch wafers, because that automatically gives, I don't know, double, let's say, the number of chips per wafer, and can significantly increase capacity.
Yeah, it's well, there are many reasons. So also here in Eindhoven, we are building a 6-inch plant, fab. It's done by TNO, the Dutch Research Institute. It's done for industry. So, I mean, it's not that they are going to use it that much. Well, they're going to operate it, but they do it for industry. So companies like Smart Photonics are interested in this, in 6-inch. But there are a few reasons for doing this 6-inch. First of all, it's, you know, for one wafer, you get indeed double the number of dies. That is true, right? Because you go from 4 to 6 inches, 1.5. Well, 1.5 square, it's 2.25, right? On top of that, typically the edge you have to discount. So there's also less edge. So that's also good. But also, there are two technical advantages. One technical advantage is if you go to larger wafer sites, then you can move slowly more towards the mature equipment, because you can use equipment that is normally developed for silicon. I mean, we have an ASML scanner here in the lab, academic lab. There was a PhD student in the past who had to get a PhD on the ASML scanner to make it ready for 4-inch indium phosphide wafers. There are differences, right?
Okay.
You need a special. So all the tooling out there, if you make a tool, of course, you're going to develop it for silicon, because 99% of the market is silicon, right? And you want that. So you want those kind of tooling. But all those tooling is typically, okay, maybe there's some legacy at 6-inch, but it's quite often it's 8 or 12-inch, yeah? But definitely not 4-inch. 6 inches around for silicon. So better tooling. And of course, the end result is also more uniformity. So in the end, your yield goes up.
So the bigger wafers are more uniform.
Yeah.
So going to bigger wafers is actually a yield benefit in terms of indium phosphide. Is that so?
Typically, it is, yeah.
Nice.
Because also because tooling, right? More mature tooling and processes.
I see. Yeah. So I'm for quite a while now, I think silicon wafers have been running on 12-inch, but for the longest time before 12-inch became a thing, it was all 8-inch wafers before that. And then it was 6-inch wafers before even that. So I think we have a lot of equipment from the 90s that has been proven to work really well that could be used for indium phosphide. And since 99% of the industry does silicon, I think we have a lot of these things lying around. So it's a lot of benefit going to larger wafer sizes for 3.5 in a sense.
Yeah, well, it's far more expensive. So, I mean, it's a trade-off, right?
The wafer is, there is a per wafer cost that goes up.
Well, you need a whole new fab. I mean, not the physical fab, but all the tooling, right? Because you want to benefit from that. So, yeah, that's expensive.
So the wafers themselves being expensive, but are the yields in indium phosphide reasonably high? Is this a concern that one has to keep in mind?
This is a very tricky question because it depends on the application.
Okay.
So yield, and it depends, of course, and we have to compare apples and oranges, right? So if you go to an indium phosphide fab, you come with a new idea and you're going to develop that, your yield is shit.
Okay.
That's because people have not been running the process. I mean, why is the yield high of a TSMC process? Because they run only one process.
So let's take an example of indium phosphide for telecom applications, which is as commercial as you can imagine a compound semiconductor to be. What do those wafers kind of run at? Those should be mature, right? They should be running at high volume and high yield.
Yeah, but the question is what you want out of it. So, I mean, a fab, the definition of yield for a fab is different than the definition of yield for an application. So a fab, the yield of a fab, let's take a step back. This is an issue that never comes up because most of the people are vertically integrated or they have their own process running in a fab. So they don't care about the fab yield versus the design yield because they integrate everything in a business model and they don't give you the data. But if you decouple that, if you now have fabs like Smart Photonics and you have end users that do something with an open process, right? Yeah, then it becomes an issue. But then you have to be very careful because TSMC, they don't define yield on, I don't know, if you make an RF transceiver and you have fabricated at TSMC, and you say, okay, I've designed this, it's a 100 gigahertz radar system for automotive. If it doesn't work, I don't think you can go back to TSMC. I think TSMC said our process control modules show that my metal has this thickness and this resistivity. My doping is there because it has this resistivity. My lines are okay. My critical defect is 1 part per million, per billion, I don't know, whatever they define it. So, forget it. We did our job. If your transceiver doesn't work, that's your problem.
Yeah, so this is basically like process yield versus parametric yield. Or in a sense, you can make a transistor that meets certain electrical specifications, and each foundry, like the TSMC, has maybe some specific test structures they put on every wafer. And if it passes that wafer is now yours, you have to pay for it, kind of thing. And on the other side, you've got the example of maybe somebody making a processor out of this, like Intel's famous process of binning transistors based on performance. So that's a different thing. Like they build a CPU, but what performance comes out of CPU is not really TSMC's problem. So in the same sense, if there's a pure play foundry like Smart Photonics making transistors, or making indium phosphide lasers, for example, they should have a set of criteria that they go by, correct?
Yeah.
And so
we're still growing up, so we have to figure that out. And
okay,
personally, I don't agree with how they do it now.
Okay.
Because they are a little bit too much towards the what they call the building blocks, right? So they basically define a modulator, but they don't give you the more basic data. I think that it's not a sustainable model because it doesn't work. But okay, that's a discussion between us and them. And of course, then you can think, who cares what it sounds a little bit weird that a professor and a company are discussing, but Smart Photonics comes from our group. The CTO of Smart Photonics is my office mate 1 day a week because he's part-time professor here. So we are quite interwoven. So we have an active discussion about these things, right? So it's, but I think we should shape that a little bit better. I mean, as we are running the YEPIX platform as a university, which is the European platform for photonic integrated circuits. And we are supposed to have a vision on, how the ecosystem should develop. So, I mean, it's not that we tell Smart Photonics what to do, but, we sit together with all these fabs and we think, okay, and with the designers and with the design houses and with the end users and with the software teams, right? I mean, it's not that we don't know what the ecosystem is doing. We are quite well embedded. Literally, we set up a large part of the ecosystem. A lot of things that happen in Europe, they literally come from this group. I'm not going to claim the credit for that. I was not in this group at the time. So it's not what I did, but a lot comes from this group. If you look what's happening in Europe.
That's great. That's great. Who are generally when, Smart Photonics makes these wafers, and especially the pure play foundry aspect is very interesting to me. Who are basically the premier suppliers of raw materials to the fab? I mean, I'm just talking about starting material.
No. You mean the wafers?
Yeah, the wafers. Yeah. The indium phosphide.
I know it's a bottleneck now. So I think somewhere China is definitely a big supplier.
Okay.
It's a bottleneck now. It's a really big bottleneck. I mean, some fabs have problems procuring the material.
That's fascinating.
Yeah, it's also shit. Because we cannot buy wafers easily.
No, that has a lot of implications because everybody wants indium phosphide lasers and you can't find wafers for them. That's a problem because everybody starts, like, at least the impression that I have from looking at the industry is that it is all somehow output restricted. Like how many fabs? Like you only have a 4-inch wafer and you can't get as many as you can get out of an 8-inch wafer. So there's fundamentally limited. And then you're limited by how many wafers you can run through a fab. And that's why there's a supply limitation. But what is more interesting is that there is an indium phosphide wafers shortage supply. And and the question is, who is supplying these wafers and how do we get more of them?
That is true. Yeah.
Yeah.
It's not that we need a lot, but I think there's a bottleneck. I don't know what the reasons were, to be honest. And I'm not in charge of buying here, but I do know we have problem procuring wafers at the moment.
Okay. I'll ask you one more process question, and then I have some other branched out questions we can get into. What is the largest reticle size you can make on an indium phosphide wafer? It's a 4-inch wafer. What's the largest reticle size?
You mean the mask, what you pattern with a mask, right?
Mask limitation, yeah.
Well, I mean, we use an ASML scanner, so whatever ASML has on offer. So that's typically the 2.5 centimeter by 2.5 centimeter or by 3 centimeters.
Okay.
I mean, there's no difference, huh?
Okay, so it's driven by the same limitations of silicon lines because you use the same technology then.
Yeah, I'm not sure it's a limitation. It's a few centimeters, right?
Yeah. I was only saying limitation because there is I'm used to saying the word limitation in the world of CMOS because GPUs are limited by reticle sizes. They occupy the entire field of view that is possible by a single scan. So in the silicon world, that is a problem when they make these large GPUs and stuff like that. But in the world of RF, analog, indium, like 3.5s, it's really not because things are actually much smaller. So that's a good distinction to make.
I'm not sure when you look at companies like Infinera that is bought by Nokia, right? They have pretty large die sizes. They have these, terabit per second coherent transmitters with hundreds of components integrated. A lot of these components, they are hundreds of micrometers, maybe running even into the millimeter. So they might start to hit the square centimeter level. But I don't know the details. There's actually somewhere a YouTube movie that someone bought a Infinera chip or module, and they are actually, disassembling it.
Fancy. I should check this out.
I don't know the link by heart, but there's somewhere on YouTube, there's this movie that someone actually, and I mean, not just someone, as one of those, persons who has access to an extremely nice microscope. So it is very insightful, actually. A lot of probably confidential information is now being disclosed there.
I'm going to find this and see if I can put it up somewhere. I'll share this link. It's fancy. Like looking at optic stuff through a microscope is amazing, actually. There are a lot of beautiful features like the gold in there and the optical fiber and how they couple. And it's actually pretty beautiful through a microscope.
Yeah.
It's really nice. So it seems like somebody asked me, and I've been trying to get some poll questions from people and see what people are interested in. You mentioned heterogeneous photo integration on silicon of indium phosphide earlier, right? What about quantum dot lasers? But maybe before we explain quantum dot, maybe we should explain what it is before we talk about how it could be a potential use in the future.
Yeah, well, what do you know about quantum dot lasers? You know about the details or not yet?
Let's just say no. I have a very basic understanding.
Okay, but did you do semiconductor physics, those kind of courses in the past?
Yes.
Yeah, so quantum dots are, have you ever heard of Schrödinger equation?
Yes.
Yeah, well, it's based on that. It's actually the textbook example of that. We can make active material in lasers. Active material is basically a semiconductor, and you have a conduction and valence band. We inject current, and we have the electrons and the holes in there, and they recombine. Then we have gain. In most telecom lasers at the moment, we actually use what we call quantum wells, which basically means we make these layers very thin. That means we start in one dimension, we start to quantize the energy states. That's because we start squeezing the material tighter than the electron wavelength. So that is where Schrödinger's equation comes into play. If you think about the potential well, that you have these, these functions, these sinusoidal kind of functions, that kind of stuff plays a role there. The point is, we make it very thin. We change a little bit on the density of states, and that means we can tailor the gain spectrum. With quantum dots, we basically make a point-like structure. So basically, in all 3 dimensions, we have now confined electrons. So we have complete control of the electronic states, so the energy levels, in theory. In practice, not, because quantum dots are all over the place. So they have all kind of different sizes. So you can say, okay, I want exactly that state. That's fun, but the next dot has it here, the next dot there. So, in the end, it averages out. And instead of more control, you even get less control, because it's all these quantum dots, they grow spontaneously. So it's a crystal.
Okay.
And if you then grow a material that is not exactly matched, but if you buy a bad Lego, if you buy cheap Lego blocks, right? Quite often you can put the very small bricks you can put on top of real Lego, but the larger the brick, the harder it gets.
Right.
Because 2 dots in Lego, okay, if you press a little bit, you make it fit.
Yeah.
But if you have a lot of them,
Yeah.
I mean, this one and this one, my
Yeah.
2 pinkies, right? They are absolutely speaking far off.
Yes.
So how do you make quantum dots? You have your wafer, and then you grow a material that doesn't fit. And because it doesn't fit, you don't get a nice layer. You get the same thing that on a window, you get droplets of water, because the forces that bring the water together, they are higher than the forces that want to spread it out.
Yes.
So you get small droplets, and that's a very natural way of making these dots. But the point is, it's spontaneous. So they all have different sizes, so it's all over the place. So can we tailor the gain spectrum? No, not really. So this old promise, why are quantum dots interesting? Yeah, that's a little bit gone. However, what makes it interesting nowadays? 2 things, mainly 2 things. The electrons are very much confined. Whereas normally, whether it's a quantum well, because a quantum well is maybe confinement in one direction, but for the rest it floats around. So normally in a laser, the electrons float around. They can just go diffuse everywhere. But in a quantum dot, they are locked.
Okay.
And that has 2 advantages that we utilize and that become very important now. The first one is that it is far more temperature stable. At room temperature, are quantum dot the best lasers? Not necessarily. But at 80 degrees Celsius, where the data centers operate, quantum dots still perform well. And for quantum wells and other materials, it's harder to do that. So they are more temperature stable. So their performance over the whole range where they need to operate, it's better. And in the past, we could circumvent that, of course, by putting a TEC, thermoelectric cooler, Peltier element. We can do that for telecom. Because then no one cares about energy efficiency, because, if you send something from Amsterdam to New York, you have to make a cable under the Atlantic Ocean. So the energy efficiency of the bits, who cares? I mean, it's all about spectral efficiency, not about energy efficiency, unfortunately. But data centers is a different story, right?
Yeah.
In data centers, it's spectral efficiency is not so much of a problem, right? Because we don't have to send tens of terabits through an optical fiber. No, we just send a few hundred gigabit through an optical fiber. We just put, a lot of optical fibers there. We cannot do that under the Atlantic, but we can easily do that in a data center. I mean, the whole backplane is optics, right? There's about energy efficiency. That means we don't want to cool the chips, and we don't want to cool the lasers. So we want uncooled lasers. And uncooled lasers means that in an environment of 80 degrees Celsius, your laser should still work. And then quantum dots come into play. So that is one aspect. Second aspect of quantum dots is, and you can see that in new companies like Quintessence, quantum dots you can grow on silicon. So instead of doing these heterogeneous integration efforts like wafer bonding, die bonding, etc., you can grow quantum dots on silicon. You cannot really grow it. It's not a nice match. So you have a lot of defects. And a defect normally is killing, because it's like having a bathtub. And if you punch a hole in it, it drains. A bathtub for the carriers, for the electrons and holes. So a laser is like a bathtub because they can go everywhere, right? So if you compare the water, it's like the electrons and the holes. If you punch a hole in the bathtub, it drains. The quantum dots is different. Think about, you take all these little plastic cups, you put them in the bathtub, and then you fill it with water. And then you put a hole in, if you have a defect, you put a hole in one of the plastic cups. But all the other plastic cups, they still hold their water, right? You can kill a quantum dot, but you have lots of quantum dots. So it's far more tolerant against defects. The defects you get if you start growing different materials on top of each other. So with quantum dots, you can actually, with gallium arsenide-based quantum dots, you can grow that on silicon. And the cool part of that is, by the way, that because the quantum dots, if you squeeze your volume, your energy levels are going to change. And you have more control of your energy level. So that means that gallium arsenide lasers, which are normally not so useful for the telecom wavelengths, with quantum dots, they are starting to enter they can do the 1300 nanometer band. So the O band.
It's great. I was going to ask you about whether you engineered a wavelengths in quantum dots, but it seems like you can get it to work at 1300 nanometer, which is
gallium arsenide quantum dots. You can get it to work at 1310, the O band, not the C band, but the O band.
That's very good to know, because that's where all of this data center stuff is definitely being used. But I had one other application. So in quantum dots, I think the way you describe quantum dots makes it a perfect fit for something like co-packaged optics, because they don't want to put typical indium phosphide DFB, or distributed feedback laser, inside a co-packaged optics switch, which has a giant piece of silicon burning a whole lot of hundreds of watts of power, because they are not inherently temperature stable lasers. But quantum dots overcomes that downside. They can operate. The laser can operate right next to a hot switch running there. And so that makes it a perfectly suited technology for co-packaged optics, which is a way that everybody wants to save power in data centers now. And the second thing is the fact that you can grow it directly on silicon makes it even more interesting.
Yeah, but that's some companies do that. So Quintessence, spin-off from UC Santa Barbara, from the group that I used to be. You have to keep in mind that a lot of people, they don't want the laser necessarily inside the co-packaged optics. You can also just keep them out of the system. So then you have less of an issue. And I think a lot of companies like AR Labs, they just have a laser engine a little bit to the side, so they don't suffer so much. But also don't forget a company like Intel, they have mastered the quantum wells to the level that they can also just run it. It's not possible. They can also run at elevated temperature without quantum dots.
Indium phosphide lasers?
Yeah.
Oh, okay. But still, the industry does not prefer putting lasers next to it, because why? Is it a reliability thing? Are these lasers going to fail eventually?
The industry, they are still figuring out. There is no industry at the moment. No one is using co-packaged optics, right?
It's very nascent. We have a few products coming out, but it's not widespread for sure.
Yeah. So people are still figuring out where the laser should be. People have already been discussing that for 20 years, and it changes all the time. But keep in mind, Intel can make the lasers right on top of the silicon. That is their proprietary effort. OpenLight, they work with Tower. They make the laser right on top of the silicon, right? So there are ways of doing that. But some others, they say, okay, we just take the silicon as is, and we have an external laser source. Global Foundries, they have little recesses that they make in their silicon so that you can flick chip a laser in it. I mean, that they facilitate that. I don't think they will claim this is the best solution. They just say our customers want this, so we do it. Again, I come back to the point, the fab is not responsible for the end product, right?
Yes.
So people are figuring that out at the moment. I mean, there's a company in, I think a French company is called Encoding, and they just say, okay, let's make the whole co-packaged optics fully indium phosphide with little directly modulated lasers. I mean, let's get rid of all the modulators. We modulate the laser directly.
Yeah.
So everything is sort of in flux at the moment. And the fact is, nobody's actually selling in volume co-packaged optics. And NVIDIA is even saying, we have it. We have a demonstrator. We have the whole ecosystem. They bought Mellanox a few years ago, right?
Yeah.
So everything is there. But they also say, Okay, but for the moment, copper still does the job. So we have it, we keep developing it, but as long as we can squeeze out copper, we will squeeze out copper, which makes a lot of sense.
Yeah, copper when you can and optics when you must.
Yep.
Something like that. Yeah. Yeah, that's interesting. Do you have any idea like when people might get more onto this co-packaged optics thing? Do you have any sense of how this is going? Or maybe we'll just stay in copper for the next 5 years and not even care about optics. Is that a possibility?
Well, if it would happen in 5 years, that would be not too bad. It might happen a little bit sooner, maybe. If the AI bubble is continuing a little bit more, then of course the demand is there. I mean, sooner or later this will happen, but I think it will be very careful at first. I mean, co-packaged optics, at first they start realizing, okay, let's only use it for the chips that are the furthest away, right?
Yeah.
And I think it will be quite gradual, as it has been all the time, right? So it's moving forward steadily. That's why your opening question, you said, what is new? Yeah, of course, scientifically, there are a lot of new things, but, things are moving very slowly in producing new technologies. And that sounds conservative, but it isn't, because we are talking about a technology, I mean, computing communication, that is the most advanced technology in the world. Nothing comes even close to this, right?
Yeah.
It's the most advanced technology in the world. It grows at an unprecedented speed of factor of 2 every 2 years. So if you very slowly catch up to that means you are the very, very best because that means you have been growing supra exponentially, right?
Yeah.
So if you catch up to the best technology in the world, where the whole world is working together, where ASML in the Netherlands and TSMC in Taiwan and NVIDIA in the US are working together to set pace,
Yes.
including a lot of other unique suppliers, right? And if you can squeeze in there, then even 3 decades is relatively fast. I mean, we have a Nobel Prize for graphene. Where's graphene?
Yes.
It's not delivering at all whatsoever. It's still silicon, and the only other technologies next to silicon that are being considered are still 3.5. And 3.5s are already around for, honestly, our group 20 years ago, 25 years ago, we were doing 3.5 electronics, and we stopped it because it was boring. Been there, done that. People have been doing it for such a long time.
Yeah.
Right. So we have to keep that in mind, and especially in academia, we don't have that mindset, and that's a bit of a problem for Europe, because in the US and in Asia, Taiwan, there are the big companies, so they make people aware that this pace, this time scales, this technology is important. In Europe, we don't have that, and because of that, I think we do the wrong kind of research. We do a lot of research on graphene, but no one knows how to make a transistor. Then we say manufacturing back in Europe, but there's literally no one in Europe who understands a transistor. We already look, everyone complains, academia, I don't get a job in academia. We have already for 3 years, we have a job opening for a professor to make indium phosphide transistors. Over all those years, we got one good applicant, and that person, he had a job at a big American semicon firm, and he got a job offer from another one. Eventually he decided not to come, but the expertise is not there. I mean, if I want to have a professor in graphene, I get 20-30 applicants who have Nature paper, but it's not a technology. It doesn't exist in the real world.
So it's a balance of how you can find people who would work on relatively mature but useful technologies versus fancy but not in manufacturing or have any reasonably short time frame practical use. So it's like you have two different balancing.
Yeah, I think when I work in my experience in the US, in the UC Santa Barbara, they had excellent professors. These professors, they knew what was still academically interesting, but if they would succeed with their projects, they would be able to start a tech transfer to the industry. So they're still academically very interesting, but also industrially relevant. Not so industrially relevant that the companies would do it themselves, because then you don't have to do it as academics. But it was so but that, adequately ahead of the curve.
Right.
In our field, but you can calculate that. That's very simple. We're part of the field of Moore's law, factor of 2 every 2 years. That means a factor of 30 in 10 years. That means a factor of 1,000 in 20 years. How far are companies looking ahead? Well, definitely 5, 6, 7 years with their product development. If I work on a factor of 2 or a factor of 4, 5, 6 improvement, even a factor of 10 improvement, I'm probably behind the curve, because by the time I get it funded and my PhD has been doing their work, we're already 5, 6, 7 years further. And then the companies have already that as a product on the market.
Yes.
So what should I aim for? Definitely, if you don't aim as academics for a factor of 100, you're out of the game. Maybe a factor of 100 to 1,000. But, and here's the real challenge, every Nature paper tells you it's, I'm a factor of 1,000 times better, but they do that on one subset, right? So they make the fastest possible transistors. I've seen Nature papers, we make terahertz transistors. We're going to change computing radically, but terahertz transistors already exist for 20 years.
Yes.
We can make them. We can also clock silicon at 50 gigahertz. But we don't do that because it's not efficient, and we burn the processors, right?
Yes.
So they are living in their dream world, and they only look at one metric. So what is really important is to have an idea where the technology is going, and the technology goes typically, it changes very slowly. So, basically you have to adapt to the existing technology. 10 years from now, there will not be a radical change. Maybe those co-packaged optics are there, but then it's done with chiplets and with those kind of things, 2D, 3.5D integration that already exists, right?
Yeah.
The only thing you're going to integrate then is a silicon photonics die.
Yeah.
But the silicon photonics die is the same as a silicon electronics die. There are copper contacts, aluminum, copper, whatever, you flip it. The techniques are the same, everything's the same. So that is, from an academic perspective, people say that is incremental. Obviously, it isn't. Obviously, it's a radical change, because all of a sudden we have fibers coming out of the processors and the memory. But that is the challenge we have to face.
What is your view on what really, how far out technologies one should be working on that will become relevant, or at least is in the direction of being relevant for a useful application in the future? Because sometimes, you don't know if they're relevant until it shows up. You can't really tell. But what is, in your opinion, a good direction one should follow?
Now, 2 things. I think first of all technologies are different. So, some technologies, they go, we talk now about the most advanced technology in the world, right? So academia should not work on anything closer by than 10 years. On the technology side, on the chip design side, it's a different story. On the technology, not closer than 10 years, but also not further away than 20 years. Okay. So basically in the 30 to 1,000 times better. Academia should also work. Of course, academia should work on graphene and boron nitride and all kind of new ideas, right? I'm not saying we should not do that. I'm just saying we should also work on, the more realistic kind of technologies. We should not start saying massively, okay, nature science is all leading. No, we should have a balance there. That is my plea. Not to stop the fundamental research, but to not have the fundamental research dominating the narrative. That is the point in Europe. In other continents, they have done a better job, in my opinion, in that respect. But you cannot work too far ahead. But and it's not about working ahead or not. It's about assessing what you can do in a scientific project. If you're done with a scientific project, would I be ahead of the curve, behind the curve, or too much ahead of the curve?
Yeah. You have to time it right. If
Yeah.
you don't time it right, it becomes useless. Either it is trivial or it
Yeah.
is far out science fiction. And so it becomes useless either way.
Yeah.
There's an intermediate balance to draw in academia there, right?
Yeah. And that varies from field. I mean, physicists have a different trade-off than electrical engineers. It's
Yeah.
simple. And industrial designers, they again have a different trade-off. They want something that works immediately. I mean, that's okay, but we should recognize that those things are different.
What is the one optics related technology that if you see in a journal, you will immediately turn to it and read today?
Yeah, it depends a little bit on the title. I mean, I'm still my own expertise is lasers, right? Indium phosphide lasers. So if people do something fun with a laser, something new with a laser, that definitely catches my my attention. Yes.
Okay, great. That's pretty much all I have in terms of questions. It's like we covered a lot of topics here actually. So I have a much better lay of the land of optics now, especially related to the process stuff we talked about. Like some of this information isn't easily available unless you talk to the people who work on it or have an intimate understanding of the directions in academia and industry together. So that's why this is such a useful chat, at least for me.
Mhm.
And I hope that the people who will read/watch this will find it useful too.
Yeah.
I have a kind of small but growing YouTube channel. I might put it up there. But my Substack is where most of my audience is. So maybe about 10,000 people might see it. And I'll probably transcribe this interview as well.
Okay. Yeah. I can always, I mean, I don't do so much on the social media except for LinkedIn. So if you post it there and you tag me, I can forward the link. I can share the link.
Awesome. Great talking to you. Thank you so much for your time. You must be really busy, but thanks for sitting down to explain this whole thing to me.
Thank you for this interview. Yeah, and again, send me an email or send me a message on LinkedIn. If you have it linked somewhere, then I can spread it. I don't have a big following, but I have quite technical following. So
no, that's important. Yeah, that's important. I think I want to bring the more technical people to the more broader people because I have a broad audience. And people have these questions, but they don't know how to get them answered. So I'm kind of an intermediary, a data exchanger of sorts.